understand better about the validity and usefulness of Gauss law. Well, Gauss law is one of the four Maxwell's equations that describe electromagnetism. It is actually theoretically equivalent to Coulomb's law. It is always valid in any given situation and circumstance. Gauss law will find that it is valid. However, it is mainly useful only in symmetric situations. So what are symmetric situations? Well, symmetric situations entail certain kind of symmetry. So let us say we have a point charge. We can sense that the electric field that the point charge creates is going to be symmetric over a sphere that encloses the point charge. So this is a situation of spherical symmetry. Another situation can be that of cylindrical symmetry, wherein we have got an infinite line of charge, and hence the electric field that this infinite line of charge creates is cylindrically symmetrical. Another situation can be of planar symmetry, wherein we have got an infinite plane of charge and the electric field that is created by this infinite plane of charge is symmetric in a planar sense. And hence these are the three main types of symmetries that we deal with: spherical, cylindrical and planar. Let us look at the application of Gauss's law in the case of spherical symmetry. So here we have a point charge kept, and at a distance r we have constructed what we can call as a Gaussian surface. Now this may be a real surface in space or it may be an imaginary surface. This is a sphere that encloses the point charge. We need an enclosed surface in order to be able to deploy Gauss's law. We can clearly see that if we take one small area element, then in that case the dA area element is going to be perpendicular to the surface and the electric field is parallel to the dA area element because of symmetry, and hence the angle between the two is going to be 0, and this is true at any location on the sphere. Also, because of spherical symmetry, the electric field will have the same magnitude at a distance r from the point charge, and thus when we write down the expression for Gauss's law, namely integration of E dot dA is equal to q enclosed upon epsilon naught. So here we get E to be constant in magnitude, dA is the small area element, and everywhere we get the angle between dA and E to be 0 degrees. So cos of 0, which happens to be 1. So the integration boils down to this, and that is equal to q enclosed divided by epsilon naught. Therefore, we can write down E, since it is constant in magnitude, we can take it out of the integral sign. Cos 0 is identically 1, and we just have integration of dA, which is nothing but the surface area of the sphere of radius r, that is q enclosed. So q enclosed is just this point charge q that is being kept inside divided by epsilon naught. Integration of dA we know is 4 pi r square. So E into 4 pi r square is equal to q divided by epsilon naught. Therefore, E for the point charge will be given as 1 upon 4 pi r square epsilon naught times q. So this can be written as 1 upon 4 pi epsilon naught q divided by r square, the same result that Coulomb's law states, and thus we can actually derive Coulomb's law for a point charge from Gauss's law. And if we reverse the steps, then in that case we can derive Gauss's law also from Coulomb's law, and thus we get a sense that Gauss's law, as we have aforementioned, is theoretically equivalent to Coulomb's law.